So at the bottom of the screen, there's a cell quest. That's a software we want to use. So once you open cell quest, it gives you an empty document. We don't want to use that. We already have a template. So I'm going to go to File, Open Document, and then I will go to say my document, my own directory, HQIN, and then I go to Document. Usually you have to find lab. You find the most recent template. So in our case, I'm going to find it looks like Apple 9. This one template. This is lab template. We also need to find out the instrument settings. Open document. Let me see whether there's an instrument setting here. No. Our template. Oh, instrument setting has to be open on a different page. Sorry. And then you go to Acquire, say Connect to Cytometer. Yes. Then you will see a browser, say Acquisition. In fact, you can use a cytometer now, but we often load instrument setting. Each channel has different voltage level. Different voltage level will detect the signal strength and position. So if you do, let's say you run one experiment today and tomorrow you run an experiment under different conditions, then the result will not be comparable. So you want to do one experiment in the same instrument setting. So for instrument setting, we go to cytometer. Instrument settings, and then we say open instrument setting, put instrument setting there, and then we say set. See the spinning wheel says it's setting the instrument set, and then we say done. Often when we run an experiment, we want to see a lot of windows. That window is called detectors, threshold, compensation, and status. We also want to go to Acquire and see something called counters. You probably after some practice on you will know why we need so many things. It's actually not difficult. After you run several times, it's much simpler than it appears. So don't be afraid of it. So. Oops. Now, see at the acquisition control, there is the checks and setup. If the setup is checked, nothing is recorded. So if you want to record your experimental data, this setup has to be unchecked. If you look at the acquisition, the main acquisition window, there's also say directory and a file. The directory is where you want to save the directory you want to save your data, and the file is the file name for the current sample. So I'm going to change the directory just to something. Save everything in the lab. That's by default. That's our lab. Sometimes you see Lee lab power. Sometimes I also run sample for other people, so I put them in different directory. So all of us should put in lab. And then we create every day, or every experiment we should create a new folder. So in this case, I'm going to call this 2012 May 31st. Just say practice. So create, choose, and then there's a file name. File name, I'm going to say this one just water. Okay. Now, once you want to click a file, you should put this on run. If you don't put this on run, it's click a file, it's going to give an error message say the instrument is not ready. If I can do that now, and I click acquire and say the supplemental status is not ready. And then I click run. Now let's do it again. Okay, now you see some signal there. You see FSC forward scattering. This is what they mean, forward scattering. Side scattering in the vertical direction. The laser is here, your sample is here. So forward scattering is like to cast a shadow of your sample. If I have particle, the forward scattering, there's a shadow on the screen. That's a forward scattering. And that signal is proportional to the size of your sample. Because it's shadow. You basically consider the shadow of your sample. The vertical scattering is the light that goes this direction and you detect at this angle. That's the side scattering signal. And that, if you think about why some of them cannot detect by radar, that's the same principle. It depends on the granularity, the roughness of the surface. So the more rough the object is, the more it will reflect light. Like in this case, laser. So the side scattering is proportional to the what they call granularity of the cell.
So they're kind of like a diamond that's very clear that can reflect a lot of light versus one that's kind of dingy that kind of reflects.
Philosophically it's similar, but actually it's not the same. That's the I forgot the physics concept of that. That's something else.
That is the total internal reflection. Total internal reflection of diamond is
that's a different one. That's a different reflection. This principle is the same principle why the sky is blue.
Okay.
Yeah, that's the same principle. The diamond reflection, that's a different. I forgot the term. Okay, but in this case you can see there's a lot of dust in that water. That water looks clear. There's so much dust that you will see here. So those are on log scale. You really need to pay attention to the scale. Those are log scale, 10 to 4, 10 to 1. So that means it's a very small particle on this side. If it's a cell, it will go to this window. For each cell, it often goes to here. So R1, R2, those are called gate. R1 gate and R2 gate. So in R2, we consider those as dust or just particles in the water. Yeah. Then you see FL1, FL2, and FL3. Those will be channels, detector channels. FL1 is wavelength of 530 with the width about 30 nanometers. That's green. That's green color, FL1. FL2, 585, that's actually in the orange and the red. And FL3 is 670, that's in the, what's the red, deep red or something. So FL2 and FL3 actually all appear to be red in our eye, even though the wavelengths differ by more than 100 nanometers.
What's FL4?
Okay, so I'm going to put this on setup because that's a baseline non-stand control. I'm going to change the file name to unstained sample. And then I say turn this on and acquire. See, there's a lot of E cell there. So it looks like I want to increase the gate. Oops, it's not changing. Now it is increasing. I want to gate majority of the cells are there. So that's the non-stained cell. So remember, FAC is cell size, SSC is granularity. That's cell. For some reason now we see very few dust. That's a good thing. So this is FAC cell size. That's channel 1. So I have channel 2 and channel 3. So both of the channel you see the signal. You still see some baseline signal. There's no fluorescence. Those are just baseline signals. So you still see some baseline signal like 50. This is probably like also like 30 or 40. For this channel, the baseline is less than 10. It's, level 3. So that's the two-dimensional part. This is called a histogram. That's the FSC. Most of the cells are very large, so it's good. SSC, most of cell is kind of pretty rough surface too. Green channel, red channel, long red channel. It looks like there's some cutoff, but it's good because at the baseline, since you see there's nothing exceeded 10, so we know the voltage seems to be appropriate. You don't want the baseline signal very high, and then when you take the actual signal, it's going to over the range. So I'm going to pause this, actually record this baseline. Now when we're recording, we want to go to the acquire storage. I want to make sure we are recording the right one. So here I'm recording, say, for G1 equals R1 for 10,000 event. R1 is this. R1 is this square window here. That's called gate 1. That's for R1 is for gate. Acquisition will stop when 10,000 of R1 events are counted. So basically, I will count any of 10,000 dots inside of this R1 window, and then this measurement will be stopped and the file will be saved. You have to make sure you check 10,000 usually is the minimum. And for each cell, that's not a problem. For mammalian cell, very often people will have a problem to actually even get 10,000 for the signal they want. So that's okay. Click OK. I'm going to now click acquire. You can actually see how many events. That's why we put a counter here. You can, if something is wrong, you will see the counter will stop, or you see 0 there. Acquire. Okay, you see the counter. 700, 1400, 21. When will it stop? It stopped probably somewhere more than 10,000, because you see also some dot there. Those are dust. But it's not counting the dust, it's only counting everything inside of there. So you see, it stopped at 11,000. So there are like 11, there are about 1,000 outside of that.
Right, okay.
Yeah. Okay, good. So that's stuff. And then we put this one on standby. Now you need to keep track which tube you are working on. So this is the tube, and this will be the next sample. So you want to take next sample with this light cell. Yeah, with vortex, so they won't stack together. And then, pull this tube there. To keep track of things, we put this on top. And then and we want to do this as quick as possible. Pull the base aside and pull these two immediately back. Pull this aside. Pull this one back. Put this one here and switch. I'm not sure how long it takes, but doing it as fast as you can. Alright, and now always remember you want to change the file name. Otherwise everything will be stored in the same file. In the end you still don't have all the data you want. Okay, so this file will be number 1 as live cell. But we will see whether it's live or not. Hopefully live. So let's see. Like, I'm not sure right now, so I'm going to click setup just to see whether the signal is right or not. Okay, acquire. This is a live cell, so I should see no signal. I should see no red cell, very few red cells. That seems to be good. See? Red should be in channel 2 or 3.
Okay.
I see something in channel 2, a little bit, but majority of them is still in the very low range. So it seems to be this one is a live cell. So I'm going to pause this. And uncheck this and just store this data. That looks like a good signal. If there are so many cells, it stops immediately. It actually goes to 25,000. Okay, now we are going to do the second one. That will be half live, half dead, I guess.
So are all white cells going to be blue? Is that why that?
No, the blue is different things. The blue is actually shows just to highlight the peak. It's not doesn't mean it's blue.
Okay.
So this. That's this one. Keep track of the sample. Number 2. Okay. Now I'm going to change the file name. I'm going to say live deck. And then set up again. Apply. Now let's see. Oh, I forgot to put this one to wrong. Let me see. Well, it's not half, but you see a lot. Yeah, you see now that this time you see that both alpha1, alpha2, alpha1. There's a lot of cell had very strong signals. Yeah, here, these two channels, FL2, FL3. If you can picture in 3 dimensions, that's how it looks like. That's FL3, that's FL2, that's the cell size. So in this circle, that will be the dead cell. Still, it's actually probably a good thing. Even though we left all the cells there, most of them still seem to be alive. These can live for months in water. Actually, we didn't even leave them. We leave them immediate. So that's at least a longer. So, okay. So I'm going to save this file. Okay, and it saves it immediately because there are so many cells there. Once I'm not running, I put on standby. For this sample, it doesn't matter, but for many of the pressure samples, maybe make a difference. So if you look at this peak, it's broader peak now, and hopefully when we switch to the dead cell, we see a stronger peak there. Okay, I'm trying to keep track of the sample. Try to vortex the sample before you measure it, because you don't want to. If you do vortex, you may have 2 cells stuck together, and If both of them dead is okay. If one is dead, the other is alive, it'll give you an average signal. That's kind of confusing. So for this one again, I'll try to do it as quick as possible. Sorry. And always remember to change the file name. And this one will be dead. I'm going to just go ahead to acquire and see what happens. Oh, very good. That's also because I'm running out of time. And this peak does seem to be a little higher right now. Okay. So yeah, R. Yeah, software R. So after you run the experiment, just when we want to start, it look like computer just freeze. Yeah, that's a problem.